Maybe you can recall. Okay, we are live now, Manmeet?
Yes, ma'am, we are live now. We can start the session.
Okay, yeah. Ciao, good morning, namaste. A very warm welcome to all present for the second day of international series, where our guest and speaker for the today is Dr. Mauro Falconeri from ENEA, Italian Agency of New Technologies from Italy. Before I give a formal introduction of Dr. Falconeri, I will just like to take couple of minutes to describe a background of our collaboration. But before that, I would like to recite a shloka from the Gita, which says, Karmanya Vadikaraste Ma Phaleshu Kadachana. That most important is your karma, and you just do your karma. This theory I have learned from him. He is my mentor, my guru in spiritual, guru to guide the path of light, and guru for the research. Whatever I have learned, even if I have learned the spelling of Raman, it is Raman, credit goes to him. So my dear students, it is really honor for you that he has taken 1 hour time, or I don't know if he can spare more for all of you. Otherwise, getting time from him is very difficult for me. I keep on asking Mauro, little bit of your time. And he always said, I am busy. But he took a lot of time and visited India and KMV particularly in year 2009. I think a gap of how many years? 12 years. So 12 years before he came to KMV as invited speaker in our first international conference of ISM. But since then, the KMV has really traveled a lot in the scale of time, improved under the leadership of our worthy madam, Dr. Atima Sharma Dwivedi, which Mauro remembers very well, and often talk about her that she's very dynamic, supportive for the sciences or for any subject, particularly for sciences, she's very progressive. Sometimes we have to wonder that her own subject is English, but she knows so many concepts of physics. So before we move on for the interaction or discussion for Dr. Falconeri, take you just little bit virtual tour of KMV, a video tour where you can see, where you can refresh your memories of KMV. Students can also see because they're sitting at home. I think Shivani is also smiling because she would love to see how KMV has evolved during all these 12 years. So just a small video for you. Can we have the video, Manmeet? It's not coming. It's not playing. It's not playing. You have to play it first, minimize it, and then share the screen, like we did earlier. Manmeet, can you try again? Manmeet, are you there? Or otherwise, I will take to the website. Yeah, okay. No. You have to play the video, minimize it, and then start sharing the screen. Don't go to the folder directly. Okay, you leave it. I will show it from the side. No, but it's not coming up. It's not coming up. Leave it from there. You stop sharing the screen, I will show. Okay. So in that case, I will take you to just for the, it will just take a couple of seconds more because some technical hitch. It's the same website, Mauro. So you can see that even on website, we have added many things, but what I want to take you to here, college video tour. So I think the screen is visible to all the guests. Yes. Okay.
Yes, ma'am, it's visible.
I'm sure the campus that inspires. It might have taken you back to the memory lane where we have like shared many moments together, and there is a heritage memorial of Goddess Saraswati, which I think a miniature small lies on your table also, on Dr. Mauro's table.
Sure.
You want to show? Yeah, then Goddess Saraswati on Mauro's table. It's a back. You have to show the front. Yeah. And then before we move on to further, dear students, he's a luminary in spectroscopy and many other areas like nonlinear optical properties and so on. On the behalf of Principal Ma'am and all the fraternity of Kanya Mahavidyalaya, we welcome Dr. Falconeri for a virtual visit to Kanya Mahavidyalaya. So his academic credentials are really, really vast. So we have just taken a small summary that with the Italian degree in physics, my Italian is very bad, but I will try to read it out. Cum laude at the University of Rome, Spezia, in 1988, and joined INEA, the Italian National Agency for New Technology, Energy, and Sustainable Economical Development in 1990. He's a senior researcher since 2010, and he runs a laser and optical spectroscopy laboratory in the Casaccia Research Center. His research activity is devoted to applied spectroscopy, mainly in the field of functional materials using FTIR, Raman, and photoluminescence, and nonlinear optical techniques. He is lately involved in the development of ultra-fast coherent Raman instrumentation. MF has participated in several national and European research projects in the field of photonics and functional techniques. I hope that shortly KMV names will always also be there for the participation in the research project. So we are keeping our fingers crossed for the outcome. But now, without taking much more time, I invite Dr. Falconeri to address the students and staff. Thank you.
So I will share my screen, right?
Yes, yes, you share your screen.
So good morning, everybody. It is a pleasure for me to give this short talk on the fundamentals of Raman spectroscopy. But before starting, I want to deeply thank the KMV principal, Dr. Atima Sharma, and Dr. Parminder Kaur and Dr. Gopi Sharma for inviting me and giving me this opportunity. Most of all, I have to thank Gopi for these very kind words you addressed to me. I don't know if I really deserve these words. In any case, I'm deeply indebted with you. Okay. So let me briefly introduce the institution where I'm working. That is ENEA, the Italian National Agency for New Technologies.
Just a minute, just small interference. I'm sorry about it. Dear students, Dr. Falconeri said that he will take questions at the end. But what you can do while his talk, you can take the questions and drop into the chat box, because chat box is visible to him also. So whenever he wants, he can pick it up the questions and just give the answers. Okay, or we can take it at the end.
Okay, let me see.
Okay,
I don't know if I can locate the
chat box. Okay, I will tell you later.
Anyway, doesn't matter. I think I will have questions at the end of the talk, and maybe after the visit. Okay.
Okay, done. Okay, thank you.
So this is ENEA, and we actually are dealing with a number of topics which are relevant for the development of the country, Italy, and mainly, anyway, energy, environment, and new technologies. ENEA is the second largest Italian research agency with more than 2,000 employees and with several research centers in all the territory. And the largest research center is north of Rome, Casaccia Research Center, and that is where my lab is also located. My lab mainly deals with vibrational spectroscopies, that is spontaneous and coherent Raman spectroscopies, and also with IR, infrared, say, and terahertz absorption spectroscopies. Of course, we have also expertise and instrumentation for what I call ancillary spectroscopies, like fluorescence, spectrophotometry, and other, say, material science-oriented techniques. Presently, our activities are mainly devoted to the development of coherent Raman techniques for its applications to material science and biomedicine, mainly. We also do other spectroscopy, applied spectroscopies applied to material science and to other ENEA topics. Okay, now let's go into the talk. This is the outline. I will first give a brief introduction of the molecular mechanisms of Raman scattering based on classical physics, and I choose this because I don't know the background of the students, so I will stay on rather basic requirements. Then I will give a brief overview of the practicalities, instrumentation, and so on of Raman, and I will give some examples of the application of this technique. Well, Raman spectroscopy is based on inelastic scattering of light by vibrations of atoms in the matter. Inelastic means that there is energy exchange between the light and the atoms that vibrate. In this way, this energy exchange is directly related to the molecular vibration frequencies, which in simple models are determined by the atomic masses and by the bond force constants. This effect was predicted in 1923 by Alphonse Megal, and then was experimentally observed by Chandrasekhar Raman, in this collaborator, and Chandrasekhar Raman got the Nobel Prize for this, and the effect is named after him. Later, it was also independently observed by other physicists in other media, and in crystals and in gases. Using this effect, using this spectroscopy, we can therefore study the vibrational frequencies of molecules and then essentially their composition and structure. To obtain an insight into the origin of the Raman effect, we observe that when matter is subjected to excitation, an excitation field, a polarization is created via the molecular polarizability. When we shine monochromatic light on the matter, also the polarization will oscillate at the same frequency, and if the frequency is optical frequency, then the molecular polarizability will consist only of the electronic contribution, since nuclei cannot follow the rapid variation of optical fields. However, nuclei are not static, they actually vibrate and rotate because of thermal agitation. So the electronic polarizability will be influenced in general by the nuclear motion, and will also have some components oscillating according to the nuclear vibration and rotation. So we are in a situation where the molecular polarizability, besides oscillating at the excitation field, is also oscillating according to the nuclear motion. And we can see that by a simple trigonometric formula, we have new combination frequency generated equal to the sum and difference between the excitation field and the nuclear movement. So the total polarization will have new frequency components besides the excitation one. Now, these oscillation components are specific of each molecule, because the thermal nuclear motion is incoherent between different molecules. So the macroscopic polarization will actually be a kind of average over all the molecular of the molecules investigated by the light. Now it is a classical electromagnetic theory result that a variable polarization creates an electromagnetic radiation whose intensity is proportional to the second time derivative of the polarization. So if we examine the polarization, we see that in absence of nuclear motion, we have only emission at the excitation frequency, but, and this is called elastic scattering, that is light irradiated at the same incoming frequency of the excitation field. But in presence of nuclear motion due to thermal agitation, this is the new expression of the polarization, and then the radiated field has new components, which are the Raman lines of the system. The new components are at the combination frequencies. So what the result is that we have new lines appearing in the scattered radiation, and the distance between the new lines and the excitation line, the elastic line, is just equal to the vibrational frequencies of the medium. The lines appearing at lower frequency are called the Stokes lines, while the lines appearing at higher frequency are called anti-Stokes lines. Now, what we said up to now is a very simple model, and we refer to kind of diatomic molecule. Now, what happens if we have a molecule composed of more atoms? Generic n-atom molecule will have several degrees of freedom, and thus will have several vibrational modes. Each vibrational mode can be Raman active if this mode changes the polarizability. As we have seen before, the polarizability must be coupled to nuclear motion. So reversing the reasoning, we see that if nuclear motion is influencing the polarizability, then we have Raman effect. The frequencies of the vibrational modes are in the 100 to 1000 centimeters to the -1 range, and they're related to molecular bonds, force constants, and masses. While the rotational frequencies, that is the frequency, the Raman frequency due to the rotation of molecules, are in a very lower energy range. Then we see that the experimentally observed bands can be attributed to vibrational or rotational modes, and therefore Raman spectroscopy gives direct information on molecular composition and conformation. And then up to now we had what we can call a really classical picture without any use of quantum mechanics, and now I just want to sketch a very say pictorially what is the quantum mechanic description of this phenomena without going into details. Well, quantum mechanically, the Raman effect is described by interaction of a photon which excites a molecule into virtual energy states. The excited molecule can decay back, emitting a new photon, and the decay can be to the same vibrational state as before, as the starting level. In this case, the emitted photon has the same energy of the incoming photon, and this is the elastic scattering, no energy exchange. Instead, the molecule can also decay to a higher lying vibrational state. In this case, the emitted photon has a lower energy than the incoming one, and the molecule creates a new vibrational energy quantum. Also, the molecule can decay, can start from an excited vibrational state, it can decay to a lower vibrational state. In this case, the emitted photon has greater energy than the incoming one, and this is anti-Stokes scattering. I will not go, of course, into details, but the Hamiltonian of the Stokes scattering involves two interactions, two perturbations, say, to the material system. The first perturbation is the electromagnetic interaction, and the second perturbative Hamiltonian is the electron vibration, electronuclear vibration interaction. So the process is a second order process. There are two perturbations. Two first order perturbation make a second order process. Using a quantum mechanical description of the Raman effect, full calculation of the Raman cross-section, that is the probability of the event, can be calculated. And using these tools, we can recover very interesting results, such as the intensity ratio of the Stokes to anti-Stokes lines, and the dependence of the Raman cross-section on the excitation wavelength to the -4th exponent. Another brief sketch that I want to give is related to the difference between molecular scattering and Raman scattering in solids. When we go from a molecule to a solid, we go from the molecular normal modes of vibration to lattice vibration, and to the normal modes of the lattice vibration, which are the phonons. So phonons are the elementary vibrational excitations of solids, of ordered solids, and they are the so-called quasi-particles. They behave as particles with a specific energy that is the remnant of the vibrational energy, and also a momentum. So when there is the interaction between the incoming photon and the material, we need to conserve energy and momentum in the scattering process. Since in a generic solid we have acoustic and optical phonons, we can have scattering both from the acoustical branch, and this is named Brillouin scattering, and we can have scattering by the optical phonon branch, and this is the true Raman scattering. The two processes have quite a different frequency scale, so it is very difficult actually to make a Brillouin spectroscopy measurement. The apparatus, the instrument need to be really different from the Raman one, so we will refer to Raman spectroscopy only in the following. Similar to what we have seen in the case of molecular Raman, there are some modes which are Raman active, and some modes some vibrational modes which are not Raman active. And this too is the case in solids, where some phonons can be or can't be Raman active depending on their symmetry properties. Just a very fast, very quick hint to what happens in an amorphous solid. Amorphous solid has no translational symmetry, so we have not really the same phonon description as in crystals, and in this case we do not have the momentum conservation that we have in crystals. And in general, this produces larger bands and less sharp features in the Raman spectrum. Okay, this was a very basic introduction to the Raman effect, and now we go to some more practical consideration on the instrumentation. First thing that is interesting to discuss is the difference between Raman spectroscopy and infrared absorption. We have discussed Raman spectroscopy as a Raman effect as due to changes of polarizability. Electron polarizability is affected by nuclear motion, and this is the basic of Raman. To produce infrared absorption, the nuclear motion must carry a variation of the dipole moment of the molecule. This is because the basic interaction between the electromagnetic field and the matter is interaction via the dipole moment of the molecules. So if a molecule has a dipole moment that changes, then we have infrared absorption. So there is a kind of selection rule between that distinguish between vibration which are Raman or infrared active. And what happens is that the two techniques are rather complementary, and both of them have their utility in spectroscopy. Some more differences are due to the fact that Raman is due to incoherent addition of waves. So the total signal generated by the matter are the signals are rather weak because they are composition of incoherent contributions. Instead, ER absorption is a coherent process. Photons are absorbed coherently by the material, so ER absorption produces strong signals. Raman spectroscopy is a scattering spectroscopy. So Raman signals are observed on zero background. There is no electromagnetic field at the frequency where we observe the Raman. Instead, IR absorption is seen on the incoming field background. From the practical point of view, Raman spectroscopy does not require or usually requires little sample preparation. You can put just your sample under the Raman instrument and see the signal. Instead, IR absorption usually needs preparation of a pellet where the sample is dispersed into an inert salt. What are the other characteristics of Raman spectroscopy which in the end affect its experimental feasibility? Well, Raman has some difficulties because the signal intensity is very low. The typical signal intensity of Raman effect is 10 to the 4 times lower than luminescence. So to measure good quality spectra, we need long acquisition times or high power lasers, which is not always possible because high power laser can hit the sample or can damage the sample. Also, we need very good quality detectors or cool detectors to reduce the noise associated with the measurements. Another shortcoming of Raman is that the wavelength of emitted photons is very near to the elastic line. This is because the distance between the Raman line and the excitation line is equal to the vibrational frequencies, which is very small in comparison to the excitation line. So we need special filtering to remove the elastic line, otherwise the noise associated to the elastic line will cover the Raman signal. So this is how a typical Raman spectrometer is done. We have an excitation laser, which must be usually very good quality because it must be stable and with the stable power and wavelength. So, for example, a diode laser is not always good because diode laser shift in frequency with temperature, while laser must be very stable in frequency. And then we send the laser light on the sample by an optical interface, and the same optical interface is used to collect the scattered Raman light. Since Raman is an incoherent scattering process, the Raman light is emitted on the entire solid angle. So we need good collection optics to collect the most of the part of the Raman signal. The Raman signal is then analyzed by a spectrograph, but before analyzing, it must be filtered to remove the elastic excitation light. The filter used to remove the elastic line is called notch filter. Notch filter is a filter which has a sharp drop in transmittance just at the elastic line. So the notch filter transmits all the light except the elastic excitation line, that is the laser frequency. We can also use edge filters, which have their advantages. That is, edge filter is a filter which has not a drop, but just an edge of transmittance near the laser wavelength. So this kind of system is rather flexible because it can be coupled to other systems like atomic force microscopes. It can be put inside the electron microscope. On the other hand, laser selection is a delicate issue because laser must be carefully selected according to the sample. And when changing the laser, the filters must be changed. So if you have several lasers, you need several sets of filters because they are specific for the laser frequency. And finally, in general, this system doesn't allow measurement of low frequency region, low frequency Raman region. You need a different kind of filters which are rather expensive. Now we go quickly to two application examples of this technique. And the first example is, I would say, very famous, is the study of carbon allotropes. So we know that carbon can form different structures depending on the degree of hybridization of the s and p orbitals. So carbon can form one-dimensional structures, two-dimensional structures like graphite, or three-dimensional structures like diamond or glassy carbon, depending on the hybridization SP, SP2, SP3. So these structures, the carbon is usually not suitable for to be studied by infrared absorption. Why? Because all the bonds are homopolar, so they don't carry dipole moment. So when the structure vibrates, there is no change of the dipole moment, so there is no infrared absorption. And this is why Raman is the technique of choice. And here we see some examples. Each structure has well-defined Raman bands. So this demonstrates the kind of fingerprinting. If I have some carbon material, I can analyze it by Raman, and if I see sharp band, that can be graphite or diamond, and these bands are sharp because these are very good quality crystals usually. When you have disordered graphite, the features smear and widen, and we have new bands created by the disordered bonds. And also you can see if somebody gives you a gift saying this is diamond, you can put under Raman and see if it is diamond or it is a piece of glass. Another very recent interest on carbon studies is graphene. Graphene is a few layer, let's say, is few layer graphite. When you have graphite, you keep removing layers and layers. You end up with few or even single layer of carbon, sp2 carbon. And what is interesting is that using Raman, you can analyze the number of layers composing the graphene. You can see that in the graphene Raman spectra, the graphite band is constant because it is just due to vibration in the graphite plane, while there are new bands like this, which are due to the vibration between the bonds of the plane, and this vibration between plane changes according to the number of planes. So this C band is very diagnostic, so it is very useful to analyze the number of planes in your graphene sample. Another example, maybe more familiar to you, is are the silicate glasses. Silicate glasses are formed by basically a silica network, which is a glass former, which has only weak bands in the so-called high-frequency region. However, this is just the glass former, and usually some modifier is added, and a different metal oxide, which is useful to change the properties of the glass. And when you add the modifier, that is another metal oxide, you can create some non-bonded oxygen. In the silica, in the fully coordinated silica network, all the oxygen make a bridge between silicon atoms, while when you add other oxide, you can have some NBO, not non-bridging oxygen. Now what happens is that the silicon oxygen stretching vibration frequency changes according to the number of non-bridging oxygen that are present in the tetraedric structure. So you can see that if you have only one non-bridging oxygen, you have bands in this region, two non-bridging oxygen. There is a hardening of the what is called a hardening, that is a low frequency shift of the stretching frequency. So Raman spectroscopy can be used also in glasses to reveal the structure, and the structure changes due to the addition of the modifier. Okay, so summarizing, we have seen that Raman scattering can be understood by classical physics using an inelastic scattering model. However, quantum mechanics is necessary to calculate the full cross-section expression. We have seen some practicalities of Raman spectroscopy, that is instrumentation and comparison with IR absorption spectroscopy, and we have seen very brief examples of application of this technique. Now I finish showing you the lab staff. We are three. It's me plus two colleagues, Serena Gagliardi and Flaminia Londino. And then we have a bit larger group as a collaboration related to coherent Raman techniques, and made from people, from colleagues from other NEA departments. So this is interdepartmental collaboration we are having. And also I want to say that those who are interested in having a short-term visit in my lab can apply to this program that is run by International Center for Theoretical Physics.
This is the
Thank you
most
for your
interesting
attention.
link they are looking forward for.
That's good news.
Sure, they are taking pictures of this slide.
Now I think that there is maybe time for questions, and then we can have the virtual tour. What
Yeah.
to say, go?
Students, how would you like to go ahead, please? Maru, you stop sharing your screen because then I will share the video to us.
Yes.
So, my dear students, please, you can unmute yourself to reply. How would you like to go? Should we take questions now or the video tour first? Come on, reply. Manna, I can see on the screen. Yeah.
Ma'am, first we'll see the video tour.
Video tour? Okay,
Yeah.
done. So whenever you reply or you ask a question to Dr. Maru, please introduce yourself that I'm so-and-so student of so-and-so class, so that he can remember a little bit of your name, then you forget. Ask me later on, what was the name? And then he will remember the class, okay? You never know who will join whom later on. So you must introduce yourself. That's what I want to say. Okay. So I'm sharing the screen and I'm taking to you virtually the most, what is this? Wait. Okay, so it goes, just a minute. I need to close that video tour of the college. Yeah, okay, done and done. I'm taking you to the video tour. Give me one moment, please. I did it actually, I downloaded it.
Maybe I can introduce the visit, just a few words.
Yeah, yes, please go on. I'm just like trying to.
So, okay, we have this lab. We have several rooms where we have a spectroscopy and also a small chemistry lab for sample treatment and preparation. And in the visit, I will show the two labs where we have the spectroscopies. And I will start. I think Gopi will launch the.
Yes, I'm going to launch.
Spectroscopy, and then I will see the Raman spectroscopy lab.
Okay, it's visible to everyone.
We have some very.
It's visible.
Yes, ma'am, it's visible.
But I need to check the sound. So I'm just playing it once. Check the sound. Sound is clear.
Yes, ma'am.
Yes, ma'am, it's on.
Near infrared spectrophotometer.
Wait, I will start from the beginning.
To the lab. Yeah, Gopi, launch it again, please.
Sorry?
Launch it, okay.
Okay, I will launch it.
Short visit to the lab. I will only show the two rooms where we have the optical and laser spectroscopy instruments. Okay. In this room, we have some very classical instruments, like for instance, UV-Vis near-infrared spectrophotometer. That is an instrument to measure the optical transmissivity and reflectivity of samples for liquid or solid samples. Then we have, okay, this is a microscope, and then we have the Fourier transform infrared spectrophotometer. That is an instrument to measure the infrared absorption bands of samples. This instrument can work in two configurations, namely transmittance of samples in pellets. So samples are reduced in pellets and they are inserted in an infrared beam path so that the detector reveals the absorption band due to the infrared vibrations of the sample. The other way to use the infrared spectrophotometer is by attenuating the total reflectance. Instead of transmission, here we have a different sample holder which has a prism, and the infrared light bounces on the prism surface, and the sample is is kept between one of the prism surface and the plate. And each time the infrared light bounces on the prism plate, prism surface, it samples the material at the surface boundary. And then after some reflections, the light comes out. So this is actually a mean to increase the sensitivity of the measurement and also to measure very small amount of samples. You can change the prism using different infrared materials to optimize the spectral interval of interest. On this side, we have another instrument that is a fluorimeter. It is an instrument to measure the fluorescence emission of samples. It is composed by a lamp. In this box there is a high-power xenon lamp which emits white light, and then the white light is monochromatized by a monochromator which selects a narrow spectral region of the white light, and this narrow spectral region is sent to a sample contained in this box. And sample, you can see, it can be a solid sample or can be a liquid contained in a cuvette, or also powders. So when the samples receives the lamp light, it can absorb the lamp light, and then this absorbed energy can be given back by luminescence emission. So the sample is supposed to emit luminescence. The luminescence is collected by a system of mirrors, is sent to another monochromator. In this way you can analyze the spectral content of the emitted luminescence, and then there is a detector that gives the signal as a function of the emission wavelength. Okay. Always on the luminescence experiment, we have another experiment here, which is a confocal laser scanning microscope. This is a luminescence microscope where the sample is placed on a slide glass, and the laser light is sent to the sample by a system of mirrors which can vibrate. Since in this way the laser changes the angle on the objective, and then the laser light scans the position of the sample. So each time the sample is illuminated by the laser, it is supposed to emit light by luminescence. Luminescence is collected by the same objective, and then you can reconstruct a luminescence map of the sample. What is important of this system is that it has a very high spatial resolution. It can build a luminescence map with very high resolution down to 1 micron, more or less, because there is an optical arrangement which avoids the luminescence emitted other than the focal point of the laser to be measured. So this is using this confocal arrangement, you can only measure the light emitted in the focal point of the laser. In this way, you avoid all the contribution, the out of focus contribution. So you have a very precise definition of the sample emitting light. Okay, and finally, last, we have here another instrument which is actually rather different from this instruments that we've seen up to now, and this is a dynamic light scattering instrument. And in this apparatus, you can measure particle dimension in a suspension. Let's suppose we have a suspension that is a liquid containing very small particles, And so the small particles in the suspension do not settle down because of Brownian motion. So when you shine light by a laser on this kind of sample, the particles diffuse light. Each particle in the suspension diffuse light, and the light diffused by the different particles interfere each other. So there is a pattern of, say, light and dark that, however, changes because the particles are moving. So the interference will change from bright to dark according of the relative movement of the particles. And then by analyzing these intensity changes, you can go down to the velocity of the particles and finally to the particle dimension. Because the smaller the particles, the faster their movement. So by analyzing the velocity by which the scattered light changes, you can go to the particle dimension in a suspension. And this can be done for particles, for very small particles, down to few nanometers. So you can measure the hydrodynamic radius of very small particles in their medium without using an electron microscope. Okay.
Okay. I will go to the second one. Okay, wait. Is it visible to everybody?
Containing our...
Yes,
me?
Yes, ma'am.
ma'am.
Yes, ma'am.
Yes, ma'am. It's visible.
And this lab presently contains two Raman experiments. The first is a spontaneous Raman instrument. And this is the instrument on this optical table. And you can see we have a microscope with a sample movement table, automatic. And the laser light is sent through the microscope onto the sample, and the Raman light, the scattered Raman light, is collected by the same objective which sends the laser in this configuration, which is backscattering, so-called backscattering configuration or epi configuration. Then the laser light is collected, goes back, and then it is filtered by a number of filters that can be changed. It is launched in an optical fiber and then is sent to a monochromator and to the detector. What are the main parts and functions of this instrument? The main part are the optical filters, which are necessary to reject the elastically scattered light. That is, when you shine the laser on the sample, you have a large portion of light that is elastically scattered, that is at the same frequency of the laser, and you have a very small amount, which is the Raman scattered light, which is the part that you are interested in. So you need a number of filters to reject the laser light to actually see the Raman light. You can, in this instrument, you can change the laser that you use to excite the Raman. You can see now I just switched on two of the laser. We have another we show, and the two lasers are one helium neon laser. This is the red line at 633 nanometers, and then we have also a green laser, which is a frequency doubled neodymium YAG laser. Why using different lasers? Because, as you may know, the Raman cross-section increases with the excitation frequency to the fourth power. So you actually want to use short wavelength laser. So a green laser is more advantageous than a red laser. However, you have also a shortcoming, which is the possibility of excite the luminescence from the sample. When you have luminescence, you are in trouble because luminescence is very intense with respect to the Raman signal. So the luminescence photon actually can cover the Raman photon, and then you want to avoid luminescence. This is why for each sample you have to optimize the laser that you use. You have to use the shortest wavelength laser, but avoiding luminescence emission. Of course, here we have also, as I said before, another laser which is under the table, a very large laser which emits blue light, 478. So we have actually 3 lasers that we can change to optimize the laser experiment. Each time you change the laser, you need to change the filters to reject the laser, because as the laser changes the frequency, also the filters will be different. So you can interchange them here. In this experiment, we have 3 filter holders, because we can put filters in cascade to improve the rejection of the laser light and to be able to measure the Raman lines very, very, very near to the laser line. You can see this here. This is, for example, the Raman spectrum of sulfur, and you have lines down to 50 centimeters to the -1. That is, laser is very near here. And to measure these lines, you need very good optical quality filters. And this can be done with this system. Some other features of these experiments are that the sample on the table is controlled by the computer, so that we can make Raman maps in samples which are inhomogeneous. We can map certain bands. We can decide to map the presence of some vibrations. In this way, we have kind of chemical fingerprinting on the sample. The other feature is that we have a very low noise detector. This detector is a charge coupled device detector, which is, however, cooled with liquid nitrogen. This is necessary for good quality Raman, because the cooling down to liquid nitrogen temperature will decrease the noise of the detector. So you can see very, very small signal, such as the Raman signals. Okay, and this is for spontaneous Raman measurements. Spontaneous Raman is Raman which is procured by the thermal vibration of the samples. Each material at room temperature will have a population of vibration due to the thermal energy. But you can do other things to measure molecular vibration. That is, you can actually excite the vibration you want to measure. In this way, the vibration of the molecules can be all in phase or coherent, how to say. While in spontaneous Raman, the vibrations of different molecules are not correlated because they are on thermal agitation. So that each molecule is vibrating with its own phases. For this reason, when you do spontaneous Raman and the molecules are vibrating incoherently, then the total signal that we will see is not very large, because each small signal produced by each molecule will not be in phase with other molecules, and so there will be cancellation of emission. While if you excite the vibration coherently, every molecule will vibrate in phase, and the signal produced will be much intense and will add in phase. These kind of experiments that are called coherent Raman experiments can be done with these experiments on this table, which are based on a femtosecond laser. This is a titanium sapphire laser which emits ultra short pulses, and these pulses can actually be used to excite coherent Raman vibration inside the samples. What is the advantage? The advantage is the largest signal, and then the largest signal is very useful to reduce the optical power on the sample. In spontaneous Raman, sometimes you need to use very high optical power to have a good signal. While if the vibrations are coherently excited, you can reduce the optical power so that you can measure samples that can be damaged by the laser, such as biological samples. And this is basically the advantages of coherent Raman techniques. So here we have the ultra short laser is actually a rather complex laser because it has a pump laser, a laser, first laser to excite the second ultra short laser, and the light emitted by the ultra short laser is launched in this rather complicated setup, using which we can actually measure at the moment some vibrational bands and some very low frequency Raman bands. These are actually presently the main activities of our lab, because we have some funded projects to develop new instrumentation based on coherent Raman scattering. Thank you.
So we are back here after the lab visit. So we can have questions in the chat box. Students, you can type, and then Dr. Folkore, I can pick it up from there. If you don't want to type, then just simply unmute yourself, introduce yourself first, and then you can ask directly. You can decide whatever you want.
I hope everybody understood, because the quality was not so good. I think there was some, it was not very fluid.
No, it was. I think they're much more interested to visit and see. But they can unmute themselves. We haven't barred them from they can unmute themselves. But Parminder, can you take the question answers from the students if they are? I cannot see. Okay, yeah, there are. Okay. There is a question in the chat box. Mauro, can you read the chat box?
Yes, I can read it.
Okay. Yeah,
okay.
please.
Yeah, I would say spontaneous Raman. Living means must be the sample must be fixed somehow, because I'm afraid an insect will move. Anyway, spontaneous. The main problem, I think, is that you have to reduce a lot of the optical power, because living otherwise you can damage the living cells. Okay, let's refer to living cells, because an insect is an ensemble of cells. Okay, any animal is an ensemble of cells. So yes, you can study living cells, but especially, but you must take care to not damage the sample. So because the laser light can induce several phenomena, the oxidation or thermal phenomena. So in the last analysis, you need to use low power lasers infrared lasers because they are less damaging. Most of damage is done by visible or short wavelength laser, so you need to go to infrared. And when you go to infrared, the Raman signal is low, and then usually coherent Raman techniques are better because, as I said in the visit, when you use coherent Raman, you have much larger signal, and then you can reduce the amount of power on your sample. Okay, so yes, living cells can be analyzed by Raman. Cool.
Sorry, Isha, please come back. Give Isha to spotlight. Isha, you must introduce yourself first because I don't want Mauro to leave with the just names, okay? He should know that we have students who are curious, they're intelligent, they're interactive.
Hello, sir.
Our
My
students.
name is Isha Bhardwaj. I'm a MSc student. So yeah,
KMV, yeah.
I feel very nice to meet you.
Thank you, Isha. Can we have Mannat on the screen, please, Manmeet? Mannat, because I see a question from Mannat Sharma. I'm taking in the order wise. So, Mannat Sharma, ask your question.
Hello, good afternoon, sir.
Good afternoon.
So I'm very glad and inspired to meet with you.
Thank you.
So my question is, how Raman effect can be used as a fingerprint of a substance or in medicines or biology?
Yeah. So fingerprinting is when you don't know what you have in your sample, you make Raman measurement, you find some bands. Then you see the frequency of these bands and you compare with tabulated results. Usually each substance has been already analyzed, and so you have in the literature, in the scientific literature, you have tables where you have frequency and corresponding sample composition. So when you have any material, usually you make the measurement and then compare with the assignment of the bands in the literature. This is fingerprinting. Otherwise, if you are dealing with material you don't find in the literature, you can get a pure sample, then you measure, and then you use that measurement as a reference. You can buy the reagent. Okay, you buy the reagent, yeah, then you measure, and then you go look for the reagent in your unknown sample. And this is fingerprinting. So in any case, you need to start from some work somebody already did. That's the band assignment. You need to look into the literature, you see a band, the frequency, and then you go and see which are the assignment for that band.
Okay. Thank you, sir.
Welcome. You're muted, Shivani.
Unmute, sir, yourself.
Good afternoon, sir. Thanks a lot for your lecture. My question is, you mentioned that we need to cool the detector for Raman spectroscopy. How cooling can enhance the sensitivity of the detector?
Yeah. Cooling enhances the sensitivity of the detector because it reduces what is called dark counts. No, when the detector is at the ambient temperature, there are anyway electrons excited by thermal agitation.
Okay.
And so these electrons give some background signal, say. But the main problem is that we associated with the background, we have a noise. So these dark counts fluctuate. And this fluctuation actually acts as noise in respect to Raman signal. When you cool the detector, the number of counts and the noise are strongly reduced. Okay.
Yes.
So if you, for example, if you don't cool the CCD, you end up with several thousand or tens of thousand counts. When you cool it down, you end up with few hundred counts. With very small noise, and you can measure really few counts of signal. Say in our lab, you can measure 2-3 counts per second. That is 2-3 photons per second. So it's very, very small very small signal, and this is why you cool. You can cool by liquid nitrogen. That is, say, the best option, but it is not so practical because you need the viewer and so on. Or more modern detectors use thermoelectric stages. That's junctions that can create a big temperature difference. But you need, say, two stages, two thermoelectrical stages to go down enough in temperature. In our case, the detector operates at 120 degrees Kelvin degrees, very, very low temperature, just above the liquid nitrogen temperature.
Before I know it's turn of Sukhvinder Kaur, but Sukhvinder, I just will take one moment to interfere in between because I could see Sangeeta here. Dr. Sangeeta is an old association with us, of course, my very good colleague and friend, and Mauro has met her before. So I just want Sangeeta first, and then we will go back to Sukhvinder, a little bit out of the place turn. And Sangeeta is our person from KMV side for the spectroscopy. So I want the two spectroscopies to have a little bit more time. So Sukhvinder, I'm sorry for it, but we will come back to you shortly. Sangeeta, now you are on screen. So please unmute yourself. And her question you can read on the screen, or Sangeeta, you can discuss yourself.
I think I can
Discuss yourself. Okay.
Actually, my question is that if we have calculated the frequencies of vibrations of some molecule theoretically using some software, but we are not getting the same frequencies on the setup, is there any mistake in the theory, or there is some problem in the setup?
Sorry, I didn't get the question because the audio is not good. So you asked the, please repeat, sorry.
Okay, I have asked that we have calculated the frequencies using some software, vibrational frequencies of
a software for calculating vibrational modes.
Yes, yes.
Raman vibrational modes.
Yeah.
Okay, but you're not observing.
Yes,
And
yes, that's what you said.
We have do the same using the Raman spectrometer. We have analyzed the same sample using the spectrometer. But the spectrometer is not providing any spectral line, any Raman line. Is there any problem in our theoretical considerations or in the spectrometer?
Oh, sorry, which molecule is that? Can you say?
It is a polymer, polyaniline.
Polymer.
Yeah.
Okay, I think polymers are basically composed by carbon and hydrogen, oxygen. So it's a kind of polymer like that.
Yes.
So you must observe something because carbon is a good emitter and CH bonds are good emitters. So I think if you're not observing anything, then it must be some problem in the apparatus, because I expect some signal. You see some signal in any case in a polymer.
Sangeeta can send the samples to you, Mauro, in that case.
Yes, sure. You can send me samples and I can give a look. It's no problem for me. If you're interested, you can send samples.
Yeah, we can send the courier with a declaration. It doesn't have any custom value and all that these things. Because once it's a problem, we have to declare it. It doesn't contain and this and that.
I remember.
Yeah, I remember the always a declaration certificate for the customs. I can do that, Sangeeta. Just give me the samples. I will post it.
Okay.
Okay. Can we have? Sorry, I took.
It's a pleasure.
Sukhvinder was there, right? But please introduce yourself. Mauro and Sangeeta knows each other, so they don't need a formal introduction, but introduce yourself.
Okay.
Hello, sir. My name is Sukhvinder Kaur. I'm from MSc Physics. My question is that why we use the Raman, how we use the Raman spectroscopy in the synthesis of graphene oxide polyaniline composites.
Graphene oxide
Aniline composites.
How you use Raman to study graphene oxide?
Yes, sir.
I don't know really actually. Graphene oxide has CO bonds besides CC bonds. So what one does usually is try to reduce the graphene oxide, right? So you will see the CO bonds and you try to make some chemical treatment to reduce the oxide and to get the graphene. I must confess that each material is a story in itself. So you must start from the literature and see what you expect, and then you go to the experiment. So I'm really not into graphene research, so I can't be more precise. Usually people prepares graphene oxide and then reduces it to get graphene. So I expect your main task is to verify that you reduce the oxide and then you get a few layer graphene. Because many people talking about graphene, they are actually dealing with several layers, and this is not useful because that's graphite. So Raman can really help in that because graphene has a specific bands. So this is how you can use Raman for that. But I can't be more specific.
See, I'm the interpreter, so I have to see the time limit also. Can we have both the students on the screen, please? Manmeet, Loveleen, non-medical 08, something like that. Please take her to spotlight along with Mitali.
Her video is not on, ma'am.
It's on. I can see her. She's smiling. She's waiting for her turn to come.
Loveleen.
Yes, Loveleen, NM08. I don't know what, is it nanometer or non-medical or what? So can we have Loveleen nanometer 08 on the screen?
Yes, yes. Now it's
so
on.
Loveleen, it's your turn first. Because, yeah. Fastest fingers first.
Good afternoon, sir, everybody.
Hi.
Sir, my question to you is there any limitation of Raman spectroscopy?
Limitations of Raman spectroscopy.
Limitations. Okay. Limitations is first of all, you can measure only materials that have Raman active modes. So as I said before, not all vibrations are Raman active. You can have strongly polar vibrations, like for example, ionic salt, NaCl salt. This is very ionic compound, and this has no practically no Raman active vibrations. So the first limitation is on the kind of bonds. When you have polar bonds, you don't expect strong Raman signal. Well, if you have homopolar bonds, then you have you can expect a strong Raman signal. In this case, Raman is useful. Second limitation is that in any case, some materials are heated by laser, and if they are they can be oxidized or their structure can be disrupted. That is, for example, on biological materials. Biological materials are very weak under the laser radiation, so you need to reduce the laser power, and maybe Raman can be also not effective because you never reach a situation where you have good signal. No, because to have good signal, you need to increase time, acquisition time, and increase laser power. If you can't increase the laser power, you need to increase the acquisition time to have a good signal. But some biological materials simply can't stand for laser for so long. For example, your colleague asked me about living cells. If you have a living cell on a microscope glass, that will remain alive just for, say, 1 hour. Then if your measurement is longer than 1 hour, your cell will die. So in this case, in practice, you cannot measure the cell. And these are kind of limitations.
Mauro, you will miss your lunch and then you will shout on me in that.
Yeah, I have maybe 10 more minutes if there is any
I know that I know the Mensa closing and opening timings. So I'm just taking the last question from Mitali. Mitali is our MSc student. Mitali, please unmute yourself and then you.
Good afternoon, everyone. I'm Mitali, pursuing MSc Physics in KMV. First of all, I would like to thank you, Dr. Myro, to give us such a knowledgeable lecture on Raman spectroscopy. My question is that how Raman spectroscopy is useful in nanoparticle analysis?
Okay, right. This is a very interesting question, actually, because nanoparticles have a specific Raman signature. Why? Because when you have, say, let's start bulk material. Okay, bulk material has well-defined Raman bands, and if the bulk is a crystal, if the material is a crystal, these Raman bands are very sharp and well-defined. For an infinite crystal, good quality crystal, Raman bands can be as narrow as few centimeters to the -1. So you see very sharp peaks. Now, what happens when you go from a bulk to a nanoparticles? A nanoparticle can be thought as a defective crystal. So what happens is that the description of a phonon, I hope you are familiar with, is not so good in a nanoparticle, because phonon applies to a perfect infinite crystal. When you have nanoparticle, phonons are, say, disturbed by the boundaries. So what happens is that the very narrow lines that you observe in a perfect crystal are broadened and also are shifted. Broadening, you can understand why, because the perfect phonon is disturbed. So there is a broadening in energy, because the energy of the phonon is not well defined anymore. Also, you have other effects, because often nanoparticle is accompanied by stress in the structure. So the bonds of the crystal are deformed, because the nanoparticle has a very high energy due to the fact that has a lot of surface. So the surface increases the energy of the structure and brings some deformation. This deformation acts as a shift of the Raman peaks. So actually, when you study nanoparticle by Raman, you get a lot of information related to the dimension and to the stress. That's it.
Thank you, Mauro. Before we go for the formal vote of thanks, I just want to introduce you to new additions in our department, because when you visited, they haven't joined. Very dynamic, Dr. Surbhi. I can see Dr. Surbhi Sharma working on chalcogenide classes. She joined the KMV around 3 years back. Now, can we have Dr. Surbhi and Dr. Harleen on the screen? These are the new additions. Dr. Harleen and Dr. Surbhi. Yeah. So Surbhi, ma'am, if you would just like to, she works on glasses, so that's what, like maybe one day her own samples, or she will herself visit. She often travel abroad for presentations, I think, but never to Italy. Surbhi, you have to unmute yourself. You're muted, beta. And can we have Harleen also on the spotlight meet quickly? Yeah, Dr. Harleen, maybe you can discuss about your research interest yourself. Harleen, sir.
Hello, Dr. Mauro. Hello. Thank you so much, sir, for very interesting lecture on Raman spectroscopy. Sir, I work on detectors. My work in signal processing. Actually, this work that you are explaining today, I am completely out of the touch of these kind of things, because I work in electronics. But really, it was very interesting lecture, because although I am not the person of the same field, but then also I have enjoyed the things very, you explained everything very completely. Thanks, sir. Thank you.
Thank you.
Sir, good afternoon, sir. Sir, thank you very much for your valuable talk with us. I was actually rewinding your lecture during your interaction with the students also. So it was very nice to know all these things. Number of things are actually, those are not in our context. Those are not known to us. We got to know those things. Thank you very much, sir. And electron microscopy, Raman spectroscopy, near infrared spectroscopy. We actually touch these fields, but we are not into that. But we got to know a number of new things. Thank you very much for that, sir.
She will definitely come to your lab, Mauro, one day. I'm sure about it. Otherwise, I will drag her.
I hope so.
Oh,
we,
thank
are
you.
we are very happy to host people and from abroad because I like
Myself, Andy, Surbi, one day we will all march past to
let's
your lab.
hope we'll be out from COVID restrictions soon. I was vaccinated, so.
So I just wanted to, before we move on to our head of department, I just want to tell this to dear students. We have kept this exclusively for all of you. That's why limited additions are done on Zoom. And for the rest of the students, we are not taking any students from other institutions. Otherwise, even if you're getting requests that student want to get admitted so that they can interact and talk, but we are a little bit like concerned about that our own students should get an opportunity to interact and talk. So they are allowed to log on to the Zoom, and rest we are, as you can see that we are broadcasting this on YouTube. And now we have to see Mauro's lunchtime also. Otherwise, we have to post him the pranthas and curry. He is very fond of. And so we will give a formal vote of thanks. I invite my head of department, Mrs. Kaur. Yeah.
On behalf of Kanya Mahavidyalaya and PG Department of Physics, I would like to extend my heartfelt gratitude to Dr. Mauro Falconi from ENIA, Italian National Agency for New Technologies, Italy, for his very interesting and informative talk. These are really technology wonders that we are able to interact with them while sitting thousands of kilometers apart. Our faculty and students have gained a lot from his talk, from about mechanism and practical applications of Raman spectroscopy, which he has explained in a simplest and beautiful way. He has also summarized difference between Raman spectroscopy and IR absorption. The video tour to labs was really so much fascinating. Thanks a lot, Dr. Mauro, for taking so much trouble and taking your time to explain each instrument so deeply. KMV's association with Dr. Mauro goes a long way back. We are already in debt to Dr. Mauro, as he has contributed a lot in the PhDs of our many research scholars, like Dr. Ruchika, Dr. Neetu, Dr. Nancy, and Dr. Shivani.
Sandeep.
We would love to have a talk from you, Dr. Sandeep, of course. We would love to have other talks in future too, Dr. Mauro. Thank you so much. Thanks a lot. And goodbye till we meet again.
Thanks to Dr. Michael Ojoan. He is always with us for all the lectures.
Dr. Alex is
Thank you very much for your words. You're so nice, and it's really my pleasure to listen to you and listen that you also are happy about this meeting, which is not so easy because I'm not used to say this.
I'm a camera shy person, Mauro. You can see I'm a camera shy person.
Wonderful, wonderful to have you. Really, from the basics you have reached up to till research. You have really explained that journey from the very basics to the research lab.
And the next lecture, Mauro, I will suggest you to just, even if you don't get time to join on Zoom, because Dr. Ojoan is going to speak next week, same time, same day, Monday, so that you can have a trip to IAE, right? Dr. Ojoan, we are looking forward for that trip. The same, otherwise that will be on YouTube, and I will send you the link. If you can join on Zoom, it's fine. Otherwise, join on YouTube and see. I'm also looking forward for a trip to Vienna on next Monday, same time, same place, Zoom. It's like a global word now.
Yeah.
And maybe more students, more interactive students, so a little bit more time for your lunch. So grazie mille. Molto.
Welcome. It was my pleasure.
Prego.
Thanks.
Goodbye.
Bye. Ciao. Arrivederci. Arrivederci. Ciao. Thanks to all students present. I think on guest koi nahi hai. We can come by resume to Punjabi or Hindi. Manmeet, can you please